Hey folks, today we're going to do a walkthrough of how to use the WebRTC Unity plugin that I've been working on behalf of Microsoft to make it easy to use WebRTC in Win32, WinUWP, and Android apps. Theoretically Linux and Mac as well, but we haven't tested those. And so what I want to do in this video is just sort of talk through some of the components that you can leverage on the Unity side to get this stuff up and running. And so what I'm going to do is I'm just going to go ahead and head on over to github/bengreenier/webrtc unity plugin. And then I've got this project. This is a Unity project. I've got this open in Unity now, so we'll just jump over there. And one thing I'm going to do real quick before we jump into this is just go ahead and turn off my video. And that's because we're going to use my same webcam as part of the WebRTC channel. So we are going to be unable to have my cam in the video while we're recording something that uses my camera. And okay, cool. So I just want to walk through what is already here if you go ahead and open up this project. And all the useful bits are really under Unity WebRTC as far as managed stuff go. You'll notice that we do have plugins in here, and we use those for the native stuff. And so this houses the actual DLLs that we call out to be able to make WebRTC actually work. But if we focus on the Unity WebRTC stuff, we can go ahead and pop into examples real quick. And you'll notice that what I have open is the WebRTC basic signal example. And right off the bat, there's really only one unique thing in here, and that's the WebRTC basic signal example prefab. And so if we go ahead and just sort of break this down, these are the components that you need to be able to successfully run the WebRTC with signaling example. And we'll sort of talk through the core bits here, and then I'm going to go ahead and recreate it. So just real quick, all the major setup is housed on this WebRTC peer object. Think of this as a Unity representation of a single WebRTC peer, including its configuration. So we can see this one's configured to use stun as a NAT traversal protocol. We'll talk about that in a separate video, but stun is what we're using here. We're using no username and no credential of any type, especially not a password. That's because we're using unauthenticated Google stun. And we do have auto initialize and auto log errors here. These are just helpful. Basically, auto initialize will start the WebRTC underlying libraries when the Unity start hook is called on this script. And auto log errors will go ahead and proxy any errors from the underlying libraries into a Unity debug error. So that's nice to have. And we've also got the peer events and the peer video scripts here. If we drop down peer events real quick, peer events is responsible for fronting all of the underlying native events all the way up into Unity events. We don't really make a ton of use of that today. So I tend to keep this minimized. But there is some stuff that we depend on. And you'll notice in some of our other scripts that we'll actually hook onto these Unity events at runtime. So even though there's nothing listed here now, we do actually make use of this, and it's important to be able to handle events from the underlying peer. We also have the peer video script. This is kind of the heavy lifter if you're doing video. This is what does the work of reading the video frames from the underlying WebRTC connection and then writing them into an instance texture for whichever object we're using as a viewer. And we'll talk about viewers in a moment. The other thing I want to dive into real quick is the WebRTC signal controls object. And this is a sort of a lightweight script that we put together that depends on an open source signaling implementation that I wrote, which is called Node.dss. And we can see that's actually linked right here in the README. And if we hop over there, Node.dss is short for dead simple signaling. It's supposed to be a super quick and easy, not production scale way to do signaling. And we're using this just because it has a really simple interface. It's a get and a post, and so that makes it quite simple for us to set up on the Unity side of things. And so when we wire this up, you'll notice we give it an instance of that peer events type. And so here this is wired to this WebRTC peer. And then a bunch of UI components to drive the interaction. And finally, we have the address of the node DSS server and the interval at which we'll poll that server for new messages. So we're just kind of using some sensible defaults here. I've got this poll value cranked up pretty high because it makes the demos a little bit snappier at the cost of sending a lot more traffic at your signaling server. But that's a trade-off we're willing to take. And so the last thing I want to dive into here is the WebRTC video player. And so you'll notice in our scene here we have a local feed viewer and a remote feed viewer, and we're just using cubes because that seemed cool. But really any piece of geometry that is able to have a renderer of some kind that can have this YUV feed material attached to it will be sufficient. You'd use a quad or a plane or whatever feels right. And you'll notice that we have this WebRTC video player class script, excuse me. The video player script is the component that's responsible for actually writing that data from the underlying feed out to the texture. And so we'll need one of these if we're intending to use video. And you'll notice here that we'll be able to either plug in some text meshes to be able to monitor FPS at runtime, or the editor will go ahead and light up with values that sort of represent how, let's see, what's the best way to think of this? The FPS of the underlying native engine, the FPS of what we're presenting on the Unity side, and the FPS that measures the number of skipped frames. And this is sort of a measure of if the native side is going faster than the managed side. And so we'll wire those up. In this case, we have two. And if we just jump back real quick to our peer, you'll notice that those line up with these values here. So that is sort of what we're going to aim to do today. I'm going to go ahead and jump back to assets and create a new scene here. We'll call it demo video. Okay, and so we've just got ourselves an empty scene here. I'm going to go ahead and first thing, I'm going to create two planes. I'm going to use planes for video, and then I'm going to go ahead and rotate those toward us about 90 degrees. I'm just going to back off the scene camera a little bit here. I actually want that to be perfectly 90 facing us, so that these two planes can sort of act like the video feeds and look like almost like giant TVs, right? And I do want to make sure that my main camera down here in the game view, my main camera is able to see these all the way. And so I'm just going to go ahead and pull that back a little bit until those are a little bit better in frame here. And I'm going to go ahead and name them local video and remote video. And if you remember, the one thing I said is that we need to have these set to use the YUV feed material. So I'm going to go ahead and make that change. Just clicking into the mesh renderer and changing the element 0 material to the YUV feed material. And then I'm going to select both of these again and go ahead and add the WebRTC video player class to each of them. We'll note multi-object editing isn't supported today. That's basically so that the FPS work that we do here to show FPS is not aggregated, because those values wouldn't make any sense. But we should have those both set up and good to go now. We'll also go ahead and just create an empty object that we'll call WebRTC, let's do manager. And we'll go ahead and set that at the origin. No particular reason, I just like to organize my things at the origin. Okay, and we're going to go ahead and add the WebRTC script, which, if you recall, this is responsible for facilitating one use of a peer connection. And think of this as a bidirectional channel. So one WebRTC script will map nicely to these two render surfaces, one that will be local video and one that will be remote. And we can see that it's already, by default, it's set up a stun server. It's going to use Google's public stun server, and auto-initialize when auto-log errors are on. And this is just kind of to use sensible defaults, the idea being that we should be able to add these scripts and just get up and running right out of the gate. Okay, and so I'm going to add my peer events script. And again, we're just going to leave that minimized. And finally, we'll add peer video. and I'm going to go ahead and create the mapping now between the local video and remote video objects into these fields so that we're able to write out video into the correct place. And there's one final step here that I would like to eventually automate with UnityScript, but for now, there is this manual step to wire up the initialization from the WebRTC base script into the initialization of peer events. So we just add the onInitialized function call here. And once again, just dragging our self into this field, and then going to peer video in this case, and doing onInitialized. And that's necessary so that when the underlying native library comes online, we can notify our components that are responsible for emitting Unity Engine events and communicating video that things are live, right? That they can begin operation. And so with that all set up, we have everything we need to be able to actually do WebRTC under the hood. But you'll notice that if we go ahead and click play, it's gonna take a second here because it's gonna be starting up the underlying WebRTC library. We'll notice that we sort of get this like default value written to the texture, but no actual data is coming through here. And so that is because we need to set up some extra steps to be able to do the SDP handshake and NAT traversal negotiation using ICE, because without those, we're running WebRTC, but we're not actually able to communicate with anyone, which isn't so useful. And so for today, I'm going to go ahead and just use the underlying signaling example exactly as it is. I'm even going to pull this in and then just break out those controls. We have to unpack this first. How do we unpack? Here we go. Unpack prefab, pull those out, delete the prefab. And note when I say delete the prefab, I just mean from my scene. It's still down here on disk. But what that did is that just pulled out the signal controls. And you can see that down in my game view here, I now have the text field and the create offer button. Excuse me. And we have the WebRTC signal controls object here. And the only thing that's missing here is the peer events. And so I can go ahead and pull this manager component into that field, and we'll wire up the peer events. And the last thing I'm going to do is change this value to localhost for testing here. And with that, we won't see any change, right? But we may actually get some logs. I think we won't see any change, but we're a lot closer. Now we have the UI. Oh, why is that happening? Oh, because okay, we should talk about that. Let me back up for a second. Cool that my local stream is working. The reason that my local stream is working is because of what we do in the signal controls script. So let me open that up in Visual Studio real quick, and we can talk about that. And so this is, let me make this a bit bigger for y'all. This is the WebRTC signal controls script. And the interesting bit for us right now is what happens in start here. We wire up all these handlers in such a way that when events from either the peer events instance or from the UI buttons occur, we take specific actions on the underlying peer event instance. And so you can see when the event for onPeerReady is fired, we start local audio video. And to do that, we call add stream, and in this case, we pass audio false. We don't start with local audio only false. We don't start with just audio. We take audio and video off the bat. And so that's the reason that we're now able to see this local video starting up, even though we're not actually connecting to signaling yet, because it occurs just whenever the peer is ready. And we could choose to move this out into our own script and just execute this logic, whenever that script starts up. We don't have that in our sample code, but that is something that someone could easily do on their own. So let's take a step back and go ahead and set up that signaling. And to do that, we're going to go ahead and jump back to GitHub over to bengrenier/node.dss. I'm going to hit clone/download, and I'm going to copy this URL. And then using whatever shell you use, you can just go ahead and git clone that URL. For me, I actually already have it cloned, so I'm just going to change directory into the location that I've cloned it to. And just to make sure everything is installed, I'm going to run npm install. Quick note that this has a dependency on Node. If you're not familiar with Node, go ahead and take a look at the README here. It should be pretty clear how to get that stuff set up. And being that the goal of this is dead simple signaling, there's very few dependencies, and I believe it's only something like 60 lines of JavaScript. So we tried to keep this super, super lightweight. And the other thing I'm going to do here is set debug equal to DSS star. And that's going to make it so that we are able to see our debug output from this process when we run it. And so then we can start it with npm start. And we'll see our first little bit of debug output is the boot sequence. You can see we're online at port 3000. And so real quick, if we switch back over to Unity, and we go ahead and start this again, noting that we're pointing at port 3000 here. When this comes up, okay, we'll see me. Hi, everybody. And we'll see a whole lot of these GET requests coming in. And this is that polling operation. And the way that this works is by using a device ID, which you can see down here in the Unity window. And this is a Unity feature for system identifiers that provides you with a guaranteed unique device identifier. And we go ahead and just piggyback off that. And so in each of our samples, we show that value to the user. And we would expect that that's what they would type in this text field. And we use that in our underlying signaling protocol to be able to query data for our specific client and send data to a specific client. And so that's how we're able to target sending a message from peer A to peer B and not accidentally get peer C involved somewhere along the way if that's not our intention. And so with this polling, we're halfway into signaling. We just need another client that would post some data to this channel. And we would expect that data to be SDP handshake data as well as ICE NAT traversal information. And I'm actually going to stop the video here because in order for me to set that up, I need a whole different computer because I only have one AV device. And the way that it's implemented today, this is a per application exclusive lock on the audio video device. So that's something that we need to consider here. So that's all I've got. We can switch back to the cam for a second. Hopefully that that makes it a little bit clearer about how you might go ahead and use some of these managed controls. There's not a lot here. Hopefully you're getting that. We try to keep this pretty lightweight. The goal was to lightly wrap the underlying library and provide a few examples of sort of how we would use that managed API to interact with a signaling server or, execute the correct sequence of operations regardless of a signaling server. Perhaps there's a creative way to connect two clients that we haven't thought of. Hopefully this was helpful. Thanks so much for following along. If this wasn't helpful, go ahead and head on over to the main GitHub for this project, the bengrenier/WebRTC Unity plugin, and go ahead and open an issue. I'd love to try and keep this up to date as much as possible. Thanks so much. Bye.